So let's try to implement the temperature dependent viscosity model. Okay, so in that in the previous case what we adopted the non-Newtonian and Newtonian aspect. Okay, so if there is a non-Newtonian fluid, we have different model and we coded one model, and based on that we able to solve the non-Newtonian fluid flows. Okay, so in the similar line, let's try to look at the temperature dependent viscosity. Okay, so before we go towards this temperature dependent viscosity, one thing I forgot to mention is about the different solvers and how the solver is able to get that particular required viscosity values. Okay, so first understand that part and then we start exploring it. So as in the previous case, we gone through the solver and we find out three solvers that will take into account the non-Newtonian behavior. One is the non-Newtonian fluid, non-Newtonian icoform. Okay, and then we have a simple form and piezo form. So let's say go to the simple form. Okay, and wait, let me close everything. So let's go to the simple form and also open the create field. Okay, so how exactly this simple form understand that from where we able to extract this viscosity value. Okay, so if you want to understand that concept, okay, so for that few things we have to take into account. One thing is in the create field area, if you look at here, single phase transport model, we say laminar transport. Okay, so with the help of that we able to take into account the this one object creations. Okay, so laminar transport is an object and that is belong to this single phase models. Okay, and and we have to give this line inside the create field file. Okay, and then what going to happen. Okay, so with this so ultimately what happened, the single phase transport is a class. Okay, and under that class we create this laminar transport as one of the object. Okay, now when we say or when we talk about the turbulence models, what happen, we say we must require these lines. Okay, and we try to utilize this laminar transport as an object, and based on that we says the this turbulence models. Okay, so what are the turbulence model we going to adopt? Based on that, it try to look at this laminar transport as an object, and it give us what? It give us the turbulent viscosity. How exactly we are taking into account this viscosity? So for that, let's go to the simple .c file, and here from here we are calling the u equations. So go to the u equations, and here this is the place, okay, through which we are based on this object. Okay, based on this object, that object is the part of the single phase transport model. Based on that we constructed whatever base trans models, and based on the trans models we try to take the turbulence, and this is the pointer, and with the help of that we say divergence dev ref of u. Okay, so let's explore where exactly it is coded. Okay, so that gave us the idea how exactly this is happening inside the solver. Okay, so what exactly? So with the turbulence we know that when there is a turbulent flows we have a two viscosity. One is laminar viscosity and another is the Newty turbulent viscosity. Okay, so how exactly both the things take into account, let's explore this part. Okay, so let's go to the area where it is installed. Okay, so identify the lines. Okay, let me do that. Okay, so it is available here. Okay, so let me open this area where we define this particular entry. Okay, so let's go to this area, this. So if you look at here, okay, so here what we did, we says that okay, here, okay, we say virtual functions dev ref. Okay, so this is how it is defined here. Okay, and now if you look at the C file, let's see. Okay, from C file we only have a function mu. So wait a minute, we look at another entry, return. Okay, this is return the divergence, return div f incompressible. Okay, trans incompressible. So let me open this file. Okay, so it is here. So here we define it. Okay, so and then from after that what we say, when anything is called as a div dev ref, what it says is return the div dev row ref. Okay, so let's now search this row ref. Okay, and it give us the proper location where it is coded. Okay, so let's say we are here linear, let's say linear this viscosity stress models. Okay, so near viscosity stress models, and here we have this entry. Yeah, so here it is exactly coded. So we have two part, one is the Laplacian of this u ultimately, and what exactly we are getting here, effective viscosity, and this effective viscosity and the this rho into alpha into rho into effective viscosity, and effective viscosity for this is belong to the laminar part. Okay, so one is belong to the laminar part. Okay, and another is ultimately belong to the so if we look at the effective viscosity, these functions. Okay, so from here we come to know that it has a two part, one is laminar viscosity, another is the turbulent viscosity. Okay, so let's check how exactly this effective viscosity is taken care. So why I'm giving you these ideas, because it give you exactly how exactly this effective viscosity is calculated. So laminar basic effective viscosity, maybe in this location we get that value. So it is a two part of viscosity. It's stuck somewhere, wait. So laminar viscosity. Okay, so when we say nu t effective, okay, so if it is a laminar case, so look, it give you only laminar viscosity. Okay, and if it is a turbulent case, so it supposed to be added nu t in it. Okay, so I am not able to exactly give you the correct location, but if it is a laminar case, it give you the nu only, even though we have a nu effective from here. Okay, so that is coming from that side. Okay, and wait a minute, it is a give you the nu. Okay, so we require that location from where we come across this nu t les effective nu t incompressible return nu f. Okay, nu t laminar at h, it is here, it's just initialized in h file. Okay, it is not there. Here we have object name nu t, but we are not taking into account the turbulent viscosity in it. Okay, so turbulent viscosity is depending on the Rans models. Okay, so let me do it again. Okay, so from here we return the nu t. Okay, k epsilon nu t les nu t scalar Chalmers Reynolds stresses. Okay, here it is using only. Okay, so nu t divergence Reynolds stresses. Here also it is using supposed to be in. This is fine. Let me find out if any new T is there. Yeah, new T is there. New T, so many places new T. So let's go to some internal areas. Okay, turbulence models, let's say RANS. Here let's try to find out the new T. So new T, yeah, so from here we are calculating the new T. Okay, but inside the code I'm not exactly getting the lines where we are combining new T and the mu together and constructing the effective, this one. Okay, so effective virtual laminar constant new only give the object of for the laminar case, laminar basic models. Okay, so if I figure it out later on, I will exactly tell you where exactly it is coded. Or let me one time try it with the, let's say, our oxygen. Maybe it will help me. New T in the runs model, laminar. Let's first reach here. Says laminar part. Okay, basic laminar. From here it just define here new T. Okay, is this function returning the turbulent viscosity new T and return effective viscosity. Okay, in line number C it is saying define. Okay, from here we get the K R new effective, new T, new effective for laminar case. Okay, and if only giving nu, basic K epsilon constructed, R constructed, but where is the new T that is constructed? From here we get the, if it is laminar we say it is a laminar viscosity, and here it is effective viscosity, but it is only taking into account this thing but not into account the new T as well. Okay, sorry, I'm not able to figure it out where exactly it is coded. Anyway, later on I will go on through it and give you the exact location, but idea is that way, that from here from the U file we call this, and finally we reach the location where it is exactly coded. Okay, so this is nothing but has a two part. Okay, new effective it take into account. Okay, so this is how exactly the let's say we can take into account the viscosity. Okay, so from here if you see new, okay, so new is a functions, okay, or object of the a particular class, and with this help of the this we are calling that with the help of the pointer. Okay, and depending on the different models we try to utilize or modify this new. Okay, so that is the idea. Okay, so this new effective is virtual function somewhere, okay, but I am not able to get exactly where it is coded. Let me try one more time if I able to manage. It's supposed to straight away give you the nut plus nu. So let me try something like nut, okay, plus nu. If I able to manage, not really here also, no. So maybe they change some writing style, okay, so that's why I'm not able to figure it out, but no worry, later on I will tell you. Okay, so that is how we can incorporate the new inside the turbulence model. Okay, now the idea is that we want to modify this dependency of viscosity in some different ways. So let's go to our area. Okay, so what we want now is something like this way. So dependency of viscosity obey the following equations. So mu equal to k into del ui by del x n power minus 1. Okay, so that is something like power law, and this k that is the constant is nothing but k0 minus mk t minus t0. Okay, where k0 mk are the initial value of viscosity and temperature dependent coefficient. Okay, so we try to incorporate this k is depend on the temperature. As the temperature vary, the k vary, and because of k vary, the mu also vary. So we have to modify or incorporate this change inside the our new temperature dependent viscosity model. So let's try to code that, and for that what we going to do, we try to add up the some available non-Newtonian models. So let's go to the area in the src folder. So that is available inside the transport models incompressible visco model, and let's add up with the power law. Okay, so go to here, let's say paste it, and in case of the power law, okay, what we say is we rename this as a something like a temperature dependent model. Okay, so let's say temperature dependent power law, we try to give that type of the name. Okay, so rename it as a 002, wait a minute, 002 temperature dependent power law. Okay, so that is the name I want to adapt. Okay, so immediately change the name to both our files first. Okay, I going to add up the make file straight away from this area because it is working, so we need not to worry that part. So from the previous models, I straight away adapting that file. Let me delete this. Okay, files, in case of this I say let's say temperature dependent power law .c is the file name what we gave. So here name is also temperature dependent power law lib, that is the name I adapted here. So let me first clean everything. Okay, so we are set with this. Let me open this area. In case of this power law, I'm changing to the temperature dependent power law in this document everywhere, same way in the C file as well. Okay, so with the help of that we are set with this all the entries. Okay, so before go for further modification, let's check the template is working or not. So let's go to that area. Okay, so temperature dependent power law. So we modify that. Okay, now our required library is set. Now what we want, we want the new few variables. One is definitely we have to have the temperature. Okay, and then along with that, what is required is we must also have a few new variables like k0. Okay, then k0 required. Then we also required this mk, that is the, let's say, something like another constant. Okay, so that is what we needed, mk. So k0 mk, and some particular T0 is the base temperature. Okay, so we required few things, so we have to adapt few of these values inside the appropriate locations. Okay, so we require the k is a function of k0 mk t. So k0 mk are initial value of viscosity and temperature dependent coefficient. Okay, so temperature dependent coefficient is mk. Okay, and k0, so let it be k0, then mk, and t as a one of the t is we have to read from our flow field, and T0 is some base temperature. Okay, so initial temperature or base temperature. So let's try to create few variables first in the .h file, and then we try to add up these things. So let's go to the .h files. So here right now I'm not changing anything, but I'm just adding few entries. Okay, so what needed, we required few things like k0. Okay, so based on this we required k0 mk and t0. Okay, so let's try to figure it out, few things here. So I'm adapting at the end here. So I say k0 I created, then mk I created. Okay, k0 mk, and then t0. Okay, so this few things we are developing, t0. Okay, so k0 t0 mk. So these three variables I want to set inside our .c file as well. So k0 mk and t0. So first let's here nothing I can do, but here I can adapt it. Okay, so let's say in the similar line whatever we have previously. Okay, so what I did previously in the similar line, I want everything to be given as a sum of the let's say like in the similar fashions. Okay, so I'm changing this based on our understanding. So I don't want that we can fix the its dimension here. Better we can specify the dimensions. Okay, so what we do, let me check it here. Fine. Okay, so what I'm doing is I am changing this entries. Okay, so in case of this way, what I want the way I develop in this particular model. So I says that something like this way. Okay, so in case of this, okay, so I say k whatever is needed, so it is the part of temperature dependent, look for it, that's it. I say look for k. Okay, then I say look for n, look for n. Fine. then I say look for n min. I'm just changing the styles. Okay, so I am sure that whatever the unit I want to specify, straight away able to specify it, okay, inside the transport property file. Okay. So this is, I am set with these variables. Now along with that, what I required few more, like a k0 new entry, then let's say mk, and then I required t0. Okay, so with the help of this I am set to read this in the similar line. Let me also keep it here, say k0 mk then t0. Okay, so all this variable is set at present. So before we go for modification, let's compile it again, check either we have any error. No error. So we are set with all the variables. Now let's modify this area of exact code what we adapted here. Okay, so everything is fine here. Okay, in case of k, what we have here, in case of the k, we have a k0 minus mk into t minus t0. So what is needed, we require the t as a new variable or new field. Okay, and that field we want to adapt from the our actual data. So what I say let's say constant, and that is nothing but volume scalar field. Okay, it is by address we want to take. So t equal to, we say u underscore dot mesh. Okay, so that is the mesh we have. Okay, u underscore mesh. Okay, this thing dot, we say lookup object. Okay, and what type of object we are looking at? We are looking at a volume scalar field. And what is the object inside the solver? Let it be a t. Okay, so with this, what going to happen, we are adapting the new t as a temperature dependent or some another this volume scalar field. Okay, and we are using this u mesh. So let me find out the exact entry inside the OpenFOAM. Let's say src grep minus r. Let me check. Look object, maybe I can check. Lookup object. Oh, sorry, my fault. src. Then I want inside the transport property, okay, anything that will give me something like a this u underscore dot mesh. Okay, so it is here inside of Newtonian fluid, that is fine, but do I have anything that will give me lookup? Okay, so it is here. Okay, lookup directory default to phase lookup object lookup object. Okay, so I think so lookup object like a volume scalar field. Okay, lookup object like a volume scalar field. Yeah, so mesh dot lookup object like this, mesh dot lookup object like a volume scalar field. So I think whatever the way I noted down is going to be correct. Let's see. Okay, what it says, template argument is invalid, like this way. So let me see lookup object for volume scalar field constant ft, and inside the mesh, let's see, if we try to add up this, it's supposed to work. Lookup object as a t. Okay, in case of this, let's say mesh dot only. With the help of that, I think I am set with the command. If it's compiled, we are set. Says volume scalar field mesh was not declared in the scope. Fine. So surface field we have, correct. Okay, so mesh was not declared in the scope, but u dot mesh, I think that was correct because we have a u as an object. Okay, so because we are using this u here, so that object we have. Okay, so based on that object, why I cannot construct this? So let me look at again. U, we have a u as a object here, u underscore mesh. Okay, and lookup object volume scalar field t. U mesh is not declared in the scope. Okay, that is correct. U mesh is not declared in the scope, but U mesh dot required. Okay, now was not volume scalar field. Oh, typo error. That is why. Fine, unused variable t, that is correct. So we are set with the syntax. Okay, so sometime we have to add up the syntax, but I know from the old style that syntax. Okay, that's why I wrote there. Okay, but we have to look at the newer style sometime. So we are set with this t variable. So now what we want inside of, in case of this k, okay, that is if we have a k equal to this, that is a power law. So in case of the k, we replace the k with the k0 mk and t minus t0. So similar thing we have to code it here, that's it. So in case of the k, we say what is that k, it is not now k, it is what, let's say function of this k is become k0. Okay, so how it going to happen, k0 minus of mk, okay, star into bracket we says that t minus t0. Okay, so with the help of that we are set with this entry, we are set with this and power of this everything. So other thing I think we need not to change, let it be everything same. Okay, so we are set here. So let's now compile it. t0, that is correct, we have a t0 underscore, so that is why it's saying not available. So with the help of that we are set with this one library. Okay, so that is how one can construct the different class of libraries based on requirement. Okay, and to run the case you try to develop the test case, whatever we have previous test case, in that we have to go ahead and add up the temperature. So let's try to do that. So we are set with this library creation. So now what we require, we have to also add up the solver. So if you look at the simple form, okay, so let's go back to the install area. Okay, so simple form, it allows us to take into account the non-Newtonian behavior of any of the fluid. So let's first add up the simple form, and inside the simple form try to incorporate the temperature equations. Okay, so let's have a let's give the same name as 002, okay, because it belongs to the same part, and here it is temperature dependent. Okay, so temp, yeah, let's say heat equation q simple form, heat simple form, that is better idea. So let's heat simple form. Okay, so what we do, we try to incorporate the temperature in it. Okay, so let me better rename as a third only. Okay, so this is library and this is the our part. I don't want either of these, let's delete that part. So fine, so now heat simple form, so let's rename it. Okay, then go to the this area. Okay, file, also rename as a heat simple form, and let's say user. Okay, so we are set with this heat simple form. Now before we incorporate the energy equation in it, let's try to compile it. Okay, so we make sure that it working fine. This is the executables, so we need not to write the wmac libaso. So fine, so we are set with this. Now what we have to do, we have to incorporate the energy equations. So energy equation is what, nothing but simple transport equations. Okay, so for that what is required, we require the new t equation file. So let me construct this one t equation file. Okay, rename it. Okay, and inside the t equation file we have to add up the transport equations. So let's say fv scalar field, or just open the transport equation and have an idea. Okay, so go to this scalar transport, go to this area. Okay, so if we want, we straight away try to add up this. Okay, so temperature, I suggest let's straight away try to add up this temperature. Okay, and if you want the non-orthogonal correction for simple, try to adapt inside the temperature equation as well. Okay, so here is this u equations, I want t equation. Okay, inside the t equations, let's say this is available. Okay, and these equations I suppose to utilize. Fine. Okay, so and it is a steady state, so no need to have a temporal term. Laplacian dt is the thermal diffusivity, so let it be same. Okay, and then if you don't require any options, let it be options available. So let's look at the generalized way of these equations. Okay, and what else we required? We supposed to keep these equations. Okay, so I think this is not required because it's already available there. Here, why I say not required? Because it is available. Okay, so if later on if we think it is not converging or something, we try to incorporate that. Otherwise, only one time I want to solve the energy equations or heat equations. Okay, so I incorporate the temperature equation. Temperature equation is here with the Fv. dt is the our thermal diffusivity. Okay, so what else we require? Changes inside the create field. We supposed to have a that reading the dt thermal diffusivity, that part is required, and the this temperature we have to read. So two things required, so let's add up that. So we are reading the temperature inside the create field of our area. Fine. So here we are reading the temperature. Along with that, what is needed, we require this transport property. So let's say read this, read the transport property. Okay, so straight away I'm adapting whatever is available there. Okay, so let's read it. Anywhere you can do that. Okay, so maybe before create field, that is better place. Okay, so reading the dt from the transport property area. So dt is set. I think we are set with this, so let try to check whether it's working or not. So transport property we read. Okay, so simple hit simple form is ready to go. Now what we require one test case so that we have to check the variations. Okay, so let's look at the temperature. Let's try to add up one test case here. Okay, so here go to the area, sorry, from this. Okay, and test case, I already have a temperature dependent this test case, but let me give the name as a this one only, so that is better name. I gave based on the library, as compared to that this is better. Okay, and from the constant file, first let's add up that library. Okay, so whatever the library we constructed, we supposed to have that library name. So what is that name we gave? It is available inside the our code option files. Okay, so this is the name we adapted, so let's add up this name over here in the control dict file. Okay, so we are set with this, and we gave the name as a heat simple form, heat simple form, that is our solver name. So now what other changes required? If you look at this two files, we come to know that few of the properties we are reading. Okay, so we are looking for all these entries. Okay, so one thing I didn't change is no more the k is required because I'm not using k anywhere. So let's get rid of the k. Okay, that is good idea because k is no more we are using. So let's get rid of the k from both the files, from here as well as from here. So unnecessarily we need not to read one more variable from our transport property area. And let's recompile it again. So let's go to 2. So because I changed the code, so look for some more places it is available. Here it's still there, so let me clean that area. So k we no more using, so I don't want that any hanging variables, that's why I deleted that part. Okay, so that is why I deleted that part from here. Okay, so k no more needed, that is fine. Now we are set, only we have to check our few values. So if you look at the transport properties from these files, we come to know that couple of the things we are reading. So like nu max, nu min, k0, mk and that t0. So all the values I set here. Okay, so k0 and mk, t0, nu min and nu max, and this is nothing but the dt, thermal diffusivity. Okay, so dt value we set. So with the help of that we able to run the test case now. Okay, so let me go to the area where we want to run it. Okay, so let's say block mesh, heat, simple form. Okay, so what it's saying, okay, so what that name of the transport models I didn't change. So our name of the transport model is this temperature. This is the name of our transport model, so I add up that name. Then temperature model coefficients is missing, that is correct, we require this name here also. Okay, now cannot find the turbulent property file. Turbulent property file is missing because the test case whatever we adapted, it is from older version. So let me add up that also. So for the simple solver, let me add up the few entries from the tutorial area. Okay, so incompressible simple form, let's adapt any one. We require the turbulence property, copy it, okay, and kept it here. Okay, and we have a laminar only, so let it be a laminar case. Okay, so that is the laminar case. So we are set with this property. Then few more entries we want to modify inside the system folder. So let's do that. System folder, fv schemes, it's saying this error, so I'm adapting this thing. Okay, because why it's gave the error, because that part is we added few more things, so for that it giving us some error. Okay, one more, Laplacian of dt not available. This is the syntax change. Okay, so previous in the new case we have a div 2, previously div only. Okay, so we required Laplacian of dt, that part is missing. Okay, then what else, cannot find k and all these things. yk and all these things required. So we want to run as a laminar only. That is laminar. Fine. Turbulence property, simulation type laminar. Save. Okay, what it's saying is that Gaussian functions supposed to be some different way, scheme wise. It's supposed to be bounded or something. Let me add up the scheme from other area and be able to set with that. That is fine. Let me check. So this error is coming because few of the entries is available inside the control dict file. So let's look at that. So if you look at the control dict file, here it's asking for this k, and k is no more we have. That's why it's giving the error. Better just switch off these functions. Okay, we not required at present for this testing. Let's see. So it's working, but it still showing some warning sign, and it is because what different type of the scheme we are using. So best part is go to this area and add up the schemes. So we supposed to have bounded scheme. Okay, so that's why it's saying this error. When we work with the steady state type of the scenario, it is better if we work with this bounded scheme. Okay, so that is what it's saying. So let me change the schemes to the bounded one, and so if it is a bounded scheme, it give us the better stability. That is what it's the idea. Okay, and let it be linear only for that purpose. Schemes. Now if you run it, okay, then Gaussian scheme, unbounded Gaussian divergence scheme. It's saying for this it is unbounded, so it's better to go with the bounded scheme. That is what it's suggesting us for temperature. Okay, and now if we try to run it again, we will not see any warning. Okay, so look, now it is clean. So what happened, we run this and then we are simulating for the temperature equations. Okay, so because it's in between starting, it's failed. That's it. Now let's see the value. Okay, so this is something like this way, and this is the values afterwards we will get. Okay, so this is the test case. Okay, how one can quickly simulate for our requirement, and here is the new, okay, as output. So if you look at the new, you will see new is not the same, it is varying basically. Okay, so so value of new is changing. Okay, but here the temperature let me check the temperature. Okay, so this is the temperature profile. Okay, and depending on the temperature profile we will see the variation in the NU as well. Okay, so that is the idea. Okay, then this is the velocity, how the velocity is varying. Okay, and here is the pressure P file. Okay, so this is something like a dummy case. Okay, just give you the idea how to add up the temperature dependency inside your solver. But if you have exact test case, you can tune this temperature dependency based on your requirement. Okay, and you can generate the test case. Okay, so right now I say mu is something like almost very simple functions, but if you have some temperature dependent function for mu, you adapt it, and depending on that function it try to modify. So normally let's say we are working with some nano fluid type of the solvers, okay, at that time we require the mu is vary with respect to some different functions, okay. Same with thermal conductivity is going to vary with some different function. At that time this concept is very very important, how to fetch this library and how to compile it and how to use that library.